Now we take up a very important article, which is displacement method. Now this method is very important and it is also a part of practical, and we have many questions based on it. So we have to go through this displacement method very carefully because there can be many questions based on it. So let's understand what is this displacement method all about. Now this displacement method is used to find focal length of any thin converging lens. Let me put it with proper stress. I repeat it again. This displacement method is used to find focal length of any thin converging lens. It's a laboratory method. Now let's understand why it is called displacement method. What we do in this method, we take an object and we fix the position of screen where image is formed. Now when I am talking about screen and image being formed on the screen, we are referring to the real image. Then we take a thin converging lens whose focal length is to be determined, and this lens is displaced between object and screen until we get a sharp image on the screen. That's why this method is referred as displacement method. Now let's go slowly and then let's understand how we determine focal length of this thin converging lens. Now we have already fixed up the position of object and the position of image, which is precisely the position of screen. Let the separation between these two is denoted by capital D, and small f is the focal length of this thin converging lens. Now we'll put the lens in between and we'll find a position of lens so that we get a sharp image. When we get sharp image, the distance of lens from the object is denoted by u, and the corresponding distance of image, that is the distance of screen from the lens, which we are denoting it by v, will be obviously d minus u. Now using the lens equation, that is 1 over v minus 1 over u is equal to 1 by f, we can rewrite this lens equation substituting appropriate values. We get 1 over plus in bracket d minus u minus 1 over minus u, and as we are talking about thin converging lens, focal length will be positive, so we will be writing equal to 1 over plus f. Now when this is rearranged, we get a quadratic equation, and that quadratic equation will be u square minus du plus df is equal to 0. Now when we solve this quadratic equation, we get two values of u. We can write u is equal to d plus minus under root d in bracket d minus 4f, this whole divided by 2. Now there are two values, so there are three cases possible. The case 1. Now in case 1, we take the situation that is d is greater than 4f. Now when d is greater than 4f, there will be two real values of u, and these two values will be distinct, and this physically means there are two positions of lens which will form sharp image on the screen. Now we move to the second case when we take d is equal to 4f. Now when d is equal to 4f, we will have only one value of u, and that is precisely u is equal to d by 2, that is the middle position. Now this means for this case when capital D is equal to 4f, we will have only one position of lens which will give us sharp image on the screen. Now the third case where d is less than 4f, the values of u will be imaginary, and physically it means there is no position of lens which can form a sharp real image on the screen. That means if we just displace our lens from object position to screen position, will not come across any position of lens that will form a sharp image on the screen. Now there are many other points that we have to understand in connection with displacement method. The whole analysis, the very first point that we need to understand, if we analyze case 1, case 2 and case 3, so we find the minimum distance between real object and real image to be formed by a thin converging lens is 4 times its focal length. So this is a very important information and it's a very important point. I repeat it again. For real image to be formed by a converging lens of a real object, the minimum separation between object and image